Good day all. In this session, we'll be seeing more about the fundamentals of fading in wireless communication. In wireless communications, fading is variation of weakening of a signal with various variables. These variables include time, geographical position, and radio frequency. Fading is often modeled as a random process. A fading channel is a communication channel that experiences fading. In this session, we'll be trying to appreciate the key concepts that underline in fading, then types of fading, models, and also the ways of mitigating this fading. Like I had mentioned, in wireless communications, fading is a variation of a weakening of a signal with various variables. These variables include time, geographical position, and radio frequency. Fading is often modeled as a random process, and a fading channel is a communication channel that experiences fading. In wireless systems, fading may either be due to multipath propagation, and this is referred to as the multipath induced fading, weather, or shadowing from obstacles affecting the wave propagation, sometimes referred to as shadow fading. The time variation of a received signal power due to changes in transmission medium or paths is known as fading. Fading depends on various factors such as rainfall, lightning, and other atmospheric conditions. In the mobile scenario, fading depends on obstacles over the path which are varying with respect to time. These obstacles create complex transmission effects to the transmitted signal. Considering various channel-related impairments and position of transmitter or receiver, there are two major types of fading in wireless communication systems: large-scale fading and small-scale fading. In large-scale fading, it includes path loss and shadowing effects, and in small-scale fading, it is divided into two main categories. The first one is the multipath delay spread and the Doppler spread. The multipath delay spread is further divided into flat fading and frequency selective fading. Doppler spread is divided into fast fading and slow fading. Large-scale fading occurs when an obstacle comes in between transmitter and receiver. This interference type causes significant amount of signal strength reduction. This is because the electromagnetic wave is shadowed or blocked by the obstacle. It is related to large fluctuations of the signal over distance. You can also observe this in the graphical representation. Small-scale fading is concerned with rapid fluctuations of received signal strength over very short distance and short time period. Based on multipath delay spread, there are two types of small-scale fading: flat fading and frequency selective fading. These multipath fading types depend on propagation environment. Shadowing effects are defined as the effects of received signal power fluctuations due to obstruction between the transmitter and receiver. Therefore, the signal changes as a result of shadowing mainly come from reflection and scattering during transmission. It is observed in wireless communication. Shadowing is deviation of received power of electromagnetic signal from average value. It is result of obstacles over the path between the transmitter and receiver. It depends on geographical position as well as radio frequency of the electromagnetic waves. The wireless channel is said to be flat fading if it has a constant gain and linear phase response over a bandwidth which is greater than the bandwidth of the transmitted signal. In this type of fading, all the frequency components of the received signal fluctuate in same proportions simultaneously. It is also known as non-selective fading. The effect of flat fading is seen as a decrease in the SNR, which is signal to noise ratio. These flat fading channels are known as amplitude varying channels or narrowband channels. In frequency selective fading, the bandwidth of the channel is smaller than the bandwidth of the signal. Different frequency components of the signal therefore experience uncorrelated fading. Since different frequency components of the signal are affected independently, it is highly unlikely that all parts of the signal will be simultaneously affected by a deep fade. Certain modulation schemes such as orthogonal frequency division multiplexing, abbreviated as OFDM, and CDMA, which is known as code division multiple access, are well suited to employing frequency diversity in providing robustness to fading. In later sessions, we'll be discussing more on OFDM and CDMA. Now, based on Doppler spread, there are two types of fading. The first one is the fast fading, and the second one is known as the slow fading. These Doppler spread fading types depend on the mobile speed, that is, the speed of the receiver with respect to the transmitter. Doppler spread refers to the widening of the spectrum of a narrow-band signal transmitted through a multipath propagation channel. It is due to the different Doppler shift frequencies associated with the multiple propagation paths when there is a relative motion between the transmitter and the receiver. Fast fading is represented by rapid fluctuations of signal over small areas, that is bandwidth. When the signals arrive from all the directions in the plane, fast fading will be observed for all directions of motion. Fast fading occurs when channel impulse response changes very rapidly within the symbol duration, high Doppler spread. You can note that the symbol period is greater than the coherence time and the signal variation is less than the channel variation. These parameters result into frequency dispersion or time selective fading due to Doppler spreading. Fast fading is a result of reflections of local objects and motion of objects relative to those objects. In fast fading, received signal is sum of numerous signals which are reflected from various surfaces. This signal is sum or difference of multiple signals which can be constructive or destructive based on the relative phase shift between them. Slow fading is a result of shadowing by buildings, hills, mountains, and other objects over the path. It can be noted by a low Doppler spread with symbol period less than the coherence time as well as signal variation being greater than channel variation. Slow fading results in a loss of signal to noise ratio. Error correction coding and receiver diversity techniques are used to overcome effects of slow fading. Now let us see the implementation of fading models. Now implementations of fading models or fading distributions are, you can see them above in the slide. These channel distributions or models are designed to incorporate fading in the baseband data signal as per fading profile requirements. The first model that we are going to discuss here is the Rayleigh fading. In the Rayleigh model, only non-line of sight components are simulated between transmitter and receiver. It is assumed that there is no line of sight path exists between transmitter and receiver. MATLAB provides the Rayleighian function to simulate a Rayleigh channel model. The power is exponentially distributed. The phase is uniformly distributed and independent from the amplitude. It is the most used types of fading in wireless communication. Please visit the URL shown for the MATLAB code for this model. The next one is the Raysian model. In the Raysian model, both line of sight and non-line of sight components are simulated between transmitter and receiver. MATLAB provides the Raysian function to simulate the Raysian channel model. Again, refer the URL for the code for Raysian model representation in MATLAB. The next model which we are going to see briefly is the Nakagami distribution and the Weibull fading distribution. The Nakagami distribution matches some empirical data better than the other models. This fading occurs for multipath scattering with relatively large delay time spreads with different clusters of reflected waves. Within any one cluster, the phases of individual reflected waves are random, but the delay times are approximately equal for all waves. As a result, the envelope of each accumulated cluster signal is rarely distributed. The average time delay is assumed to differ significantly between clusters. If the delay times are also significantly exceed the bit time of a digital link, the different clusters produce serious intersymbol interference. So the multipath self-interference then approximates the case of a co-channel interference by multiple incoherent, rarely fading channels. Weibull fading, named after Walidi Weibull, is a simple statistical model of fading used in wireless communications and based on the Weibull distribution. Empirical studies have shown it to be an effective model in both indoor and outdoor environments. The next type which we are going to see here is the upfade or upfading. Upfade is a special case of fading used to describe constructive interference in situations where a radio signal gains strength. Some multipath conditions cause a signal's amplitude to be increased in this way because signals traveling by different paths arrive at the receiver in phase and become additive to the main signal. Hence, the total signal that reaches the receiver will be stronger than the signal would otherwise have been without the multipath conditions. The effect is also noticeable in wireless LAN systems. Fading can cause poor performance in a communication system because it can result in a loss of signal power without reducing the power of the noise. This signal loss can be overcome or all of the signal bandwidth. Fading can also be a problem as it changes over time. Communication systems are often designed to adapt to such impairments, but the fading can change faster than the adaptations can be made. In such cases, the probability of experiencing a fade and associated bit errors as the signal to noise ratio drops on the channel becomes the limiting factor in the link's performance. The effects of fading can be combated by using diversity to transmit the signal over multiple channels that experience independent fading and coherently combining them at the receiver. The probability of experiencing a fade in this composite channel is then proportional to the probability that all the component channels simultaneously experience a fade, a much more unlikely event. Diversity can be achieved in time, frequency, or space. Common techniques used to overcome the signal fading include diversity reception and transmission, MIMO, OFDM, rake receivers, space-time codes, forward error correction, interleaving. We have seen some fading models such as the Nakagami fading, Rayleigh fading, Raysian fading. Now, these fading models for the distribution of the attenuation is not limited. There are other fading models like log normal shadow fading, Weibull fading. Now, based on your understanding, write short notes on these fading models that are listed there and post your answers in the Blackboard discussion forum. Once you have posted your answers in the blackboard, you're free to leave. And that's all for today. Thank you for listening.